Okay, so as Omar alluded to earlier, the sauropods are the pretty members of Sauropodomorpha. So these are the big long-necked megaherbivores that dominated Mesozoic ecosystems from the Jurassic to Cretaceous. They are globally distributed. They are these large-necked animals, essentially. And often we think of the late Jurassic as a sort of peak of their diversity, at least when we're taking sort of the fossil record at face value. And in particular, we're talking about the last two stages of the late Jurassic, the Kimmeridgian and the Tithonian. But these are really dominated by a small number of geographic regions. Essentially, most of this diversity comes from the Morrison Formation of the US, which includes taxa such as Camarasaurus, Apatosaurus, Brontosaurus, Diplodocus, lots of famous taxa like that. The Tender Groove Formation of Tanzania, which includes Giraffatitan and Dicryosaurus, and then a relatively small number of taxa from Iberia, and an even smaller number of taxa from South America, and fewer again from China. And actually, most of those taxa that I just mentioned, and the other sort of taxa in those formations too, are all members of the group Neosauropoda. So this is a very simplified topology showing the main sort of relationships and some sort of exemplar taxa for Sauropodomorpha. And what you'll see is all these taxa that I mentioned before are all here turning up in the late Jurassic. And essentially, we have this sort of, on face value, this sort of sudden burst of diversification in the group, with Neosauropods basically being all over the globe. And essentially, we have no record of the group before this. So this is problematic if we actually want to understand what's going on in the early evolution of the group. And I say when we look at actually the distribution of sauropod fossil occurrences, so these are the main faunas or main formations that are yielding diagnostic sauropod remains from the Middle Jurassic through to the early Cretaceous, you can see that although it's a global array of localities, it's actually quite patchily sampled. And for instance, I mentioned those ones from the late Jurassic, but the Middle Jurassic and the early Cretaceous are not much better either. So we actually have quite a sort of poor and patchy record of the group in general. Another aspect relates to how we've been sort of looking at the phylogenetic relationships of the group for the last sort of 10 years. Whereas sort of early analyses, sort of up to about sort of 2004, were focused on looking at all sauropods in general. More recently, so the last sort of 10 years, we've really been focusing on trying to understand the relationships within the main groups. So in particular, looking, in particular looking at Neosauropods, so looking at diplodocoids, the group that includes diplodocids, dicryosaurids, and rabacosaurids, and macronarians, which comprises Camarasaurus, brachiosaurids, and then the group eventually leading to titanosaurs. And so most recent analyses essentially focused on one or the other of the Neosauropod clades. So the tree at the top from Emmanuel Schopp basically is focused on diplodocoids, primarily on diplodocids and dicryosaurids, for which it's pretty much comprehensively sampled, but essentially has almost no taxa outside of diplodocoidia. Similarly, a tree from my own analysis from last year essentially is focused on sampling macronarians, so all basal macronarians, brachiosaurids, and most titanosaur forms up to the mid-Cretaceous, but samples almost no taxa in diplodocoidia and a sort of relatively small number of taxa outside of Neosauropoda in general. So neither of these trees are really sampling the other clade, and that's problematic if we want to understand what's going on with taxa just outside of Neosauropoda. So there is one example where there is both clades are represented, and this is a tree that's been sort of gradually built up by Jose Carbachido and colleagues over the last sort of 5 or 6 years. And this does sample taxa from Macronaria and Diplodocoidia, but neither part of the tree is anywhere near as densely sampled as those other trees. And there are a few sort of slightly unusual results, sort of relatively deeply nested in these trees, such as some of the taxa here in basal titanosaur forms, which don't seem to, their positions don't seem to be supported in any of our analyses. And so I think there's potentially some relatively small problems with this tree in terms of actually understanding sort of some of the character evolution around the base of Neosauropoda. And this is really sort of nicely exemplified by a number of taxa that are very unstable in these trees. So one such genus is Haplocanthosaurus, known from probably 2 species from the late Jurassic Morrison Formation of the US. Despite being known from several skeletons, representing most of the skeleton apart from the skull, we still don't actually have a clue where Haplocanthosaurus fits in the sauropod tree. It continuously bounces around between basal macronarian, basal diplodocoid, and outside of neosauropod positions. And that's the same even within one person's analysis as they sort of redo it and analyze it with additional taxa added. So with that in mind, myself and Paul and other colleagues have been revising and studying lots of remains from around from the Middle Jurassic through to the early Cretaceous, including sort of old classic taxa, as well as some new specimens too. So one part of this has been revising the Tendaguru Formation of Tanzania, this late Jurassic unit, which has produced famous taxa such as Giraffatitan and Dicryosaurus, but also a bunch of other taxa that have largely we've largely struggled to understand what they actually represent. So most of his remains have at some point been referred to a taxon eventually called Unentia. And so Unentia is based on this hind limb, and over time lots of other remains have been referred to it, but largely none of these can actually be referred based on actually overlapping material. And nearly all these remains have remained somewhat enigmatic in terms of actually what kind of clades they represent. So as part of this, we've revised Unentia itself, so recognizing a bunch of autapomorphies of this taxon and able to support some previous referrals of additional remains, so referring forelimb remains to the hindlimb remains. But now we're basically at a situation where we have a fairly good idea of what the actual appendicular anatomy of Unentia is, but we have no vertebrae that we can confidently attribute to Unentia. So it remains at the moment as a taxon entirely known from limb elements. And so the problem comes is that we have a number of additional taxa in the Tendaguru Formation. They definitely can't be referred to Giraffatitan or Dicryosaurus or the Diplodocid in there, but they don't overlap with Unentia. And one of these is this very unusual two dorsal vertebrae from the anterior end of the dorsal series, which were described by Unentia in the 1920s, but not really dealt with properly until Bonaparte in 2000. And he named these Tendaguria, but had no idea where they fit within the sauropod tree. And that's essentially remained the same problem ever since. So they're very unusual. So we went about describing them in detail. We also got them CT scanned. These are quite big vertebrae. This scale bar is 200 millimeters. So they were CT scanned at Berlin Zoo. And what they showed is that the internal structure essentially is relatively apneumatic, which is quite unusual if this was a derived sauropod, which is what some people originally thought. And so we did this work and recognized a bunch of what I thought were sort of quite unusual autapomorphies on this, but it didn't really help place it where it goes in the sauropod tree. But then last year, two sauropods came out from the early Cretaceous of the US, one Moabosaurus and another Mirasaurus, both known from most of the skeleton, and the authors of the second one basically recovered these two taxa as a sister taxon to a group of otherwise Western European sauropods from the late Jurassic, a group known as Turriosaurs. So this is a somewhat unusual and surprising position, but does seem to be relatively robust. And the most immediate aspect of when I saw this paper come out was, where have all my autapomorphies gone? Essentially, this thing, at least on a first glance, looks very similar to Tendaguria, but actually lots of the relatively subtle features of certain laminae and fossae, and also its very unusual neural spine, are shared between the two taxa. So potentially, we have evidence that Tendaguria is actually a member of this clade, an actual Turriosaur. And if it is the case, then this would be the first Gondwanan member of this clade. A second specimen that was originally referred to Unentia is a series of caudal vertebrae. So 30 caudal vertebrae and some chevrons. Again, originally referred to Unentia, but not based probably on any overlapping material. The potentially overlapping material is since lost, probably destroyed by us in the Second World War. But it has a number of unusual features. And in particular, it resembles in many different ways, more than anything else, it resembles Mamenchisaurus and other Menchisaurids, which are a clade of sauropod dinosaurs from the middle to late Jurassic of East Asia, and a clade that we've always thought of as endemic to East Asia. So some of these features are more widespread than just being present in Mamenchisaurids. So prominent procele is a feature of lots of sauropods, but the overall combination of lots of these features, coupled with this particular feature where the neural spine essentially doubles in length from bottom to top in lateral view, all seems to suggest potentially we are dealing with something that is a Mamenchisaurid. This would be relatively unusual and unexpected, but all the features do seem to suggest that potentially that's what this is. So moving away from the Tendaguru Formation, we also looked at a new taxon from the early, or probably early Middle Jurassic of northern China. This is an animal known from multiple skeletons, representing pretty much all the anatomy. And you can see here, Paul taking it very easy as normal, Omar helpfully walking on the specimen as we're working on it. But we described this last year with Xu Xing and Paul Barrett and other authors too. And we're pretty convinced that what this is a dicryosaurid diplodocoid, based on a large number of synapomorphies that seem to support that. These are present in both the skull, but also in the postcrania. And this is interesting for a bunch of different reasons. Primarily, we thought diplodocoids never ever made it into Asia at any stage of their evolution. But secondary, this taxon is about 15 million years older than the oldest previously known diplodocoid or neosauropod. So it's sort of drastically extending the range of this group, both spatially but also temporally too. So we incorporated these taxa and lots of other taxa we studied over the last few years into an expanded version of that 2017 matrix I sort of showed a quick topology of earlier. This now comprises 117 taxa scored for 542 characters. A large majority of these are scored by myself and or Paul. It includes now most neosauropods except the very derived titanosaurs, which is really the next aspect of this project. It has now a good sampling of basal eusauropods, non-neosauropods. It now has most Middle Jurassic to sort of mid-Cretaceous sauropods included. And we analyze this in TNT, using both an equal weights approach, but also using extended implied weights. But I'm just going to show the equal weights tree and the relatively similar results. They're largely congruent. So this is the agreement subtree plotted against time. I've just collapsed one of the titanosauriform nodes because I'm not really interested in showing that here. And what you can see is that tail I talked about earlier from 10 degree formation is coming out as Memenchosaurid. Both Unentia and more convincingly Tendeguria are coming out as Turriosaurs. We are seeing Haplocanthosaurus with some sort of confidence being produced as a basal diplodocoid, and our new taxon from China, Lingwulong, is coming out as a Dicryosaurid. Bremer supports are generally quite low for lots of these nodes, but that's not too surprising considering actually how fragmentary many specimens are. We are also interested in looking at the biogeographic history of the group as well. So we used the R package biogeobears that Neil Brocklehurst was talking a bit about earlier. We also incorporated paleogeographic constraints in our analyses. The very simplest level essentially saying whether one area is or is not connected to another. And we did this in a number of different ways. We did this in a sort of harsh way, where basically if there was no evidence to suggest these areas, then they definitely were not allowed to be connected to one another, but in also a more relaxed way, where we gave it a chance potentially that two areas were in connection. So this relates to things like seaways or evidence of maybe land bridges between two areas. So in a relatively simple sort of summary of their own main results from this analysis, essentially the biogeographic history of eusauropods is best explained by a combination of sympatry, early occurrences of widespread ancestral stocks, followed then by regional extinctions, and founder event speciation, essentially long-distance geodispersal. But a lot of that is masked essentially by lots of sampling failure. And the Tendegrue sauropod fauna, this late Jurassic fauna from Tanzania, is likely assembled as a result of three main phenomena linked to the radiation of lots of lineages, either in the late early or the middle Jurassic, i.e. a long time preceding the actual timing of the Tendegrue formation. And these essentially come down to likely invasions from probably Euro-America of things like brachiosaurids and turriosaurs, probably endemism in West Gondwana. So we find clades of dicryosaurids and diplodocids, and that both of these clades actually survive into the Cretaceous here as well, whereas they don't seem to survive in the northern hemisphere into the Cretaceous. And probably we have to deal with lots of regional extinctions, as well as sampling failures in the late Jurassic and later. And that means we get these restricted ranges. So that's why we get this impression that things like Memenchosaurids are maybe endemic to East Asia. So in conclusion, we think we have good evidence that Tendeguria, and maybe also Unentia, is a Gondwana member of the otherwise Laurasian clade Turriosauria. We have what we think is good evidence that Memenchosauridae is present outside of East Asia. And although that by itself might seem a little bit surprising and radical, combined with having Lingwulong, this Middle Jurassic Chinese diplodocoid, also in China, it suggests this sort of much more widespread dispersal of sauropods, including prior to East Asian isolation. And in general, the biogeographic history of eusauropods is best explained by symmetry, early occurrences of lots of clades followed by regional extinctions, and long-distance geodispersal. And it's really important that we sort of continually sample more and more taxa, more and more characters. That's a really important aspect of this. And I'll continue to do that, but ultimately, Lingwulong in particular, I think, shows that actually, if we don't sample more early and middle Jurassic faunas, and this goes also for other groups, not just sauropods, essentially, we're not going to be able to resolve lots of these problems in terms of what's going on in these sort of early radiations of these key clades of Dinosauria. And that's a real sort of important aspect. We need to find eusauropods and early neosauropods elsewhere in the middle Jurassic and perhaps earlier too. So with that in mind, I'd just like to thank these people I collaborated with, who I could have made an author but didn't, and curators everywhere. And if you have any questions, I'll happily try and answer them. Thanks.